Here this is R and this is C. Okay. So what you need to do? In the first question, the question is actually the same. That is also differential amplifier. Okay. But you can see here they provided us here a capacitor instead of resistance. Okay. So you can do this one in both the way. First, we can do in a frequency domain, or we can do in the time domain also. Okay. First, we will go with the frequency domain. Why? In the frequency domain, that is little bit easier. Okay. We assume that the impedance of this one is ZC. Okay. So first, we know that the impedance is ZC. So first, what you need to do? Apply KCL at point A and point B. Right? We can write down VA minus VI divided by R plus VA minus 0 divided by ZC equal to 0. Okay. From here we can write down VA by R plus VA by ZC equal to VI by R. Okay. From here we can write down VA into 1 by R plus 1 by ZC equal to VI by R. That means VA equal to VI by R into ZC divided by R plus ZC. That means VA equal to VI multiplied by ZC divided by R plus ZC. Okay. So I just wipe other parts and keep the ultimate formula. Now apply KCL at point B. We can write down VB minus 0 divided by R plus VB minus V0 divided by ZC equal to 0. Right? That means VB into RZC R plus ZC equal to V output divided by ZC. Okay? So ZC cancel. We can write down VB equal to V0 multiplied by R plus ZC. Okay. Here we assume that the op-amp is operating in the active region. So we can apply virtual short. Right? That means VA will be equal to VB. If we use this formula, then we can write down VI multiplied by ZC divided by R plus ZC equal to V0 multiplied by R divided by R plus ZC. R plus ZC cancel out. We can write down V0 will be equal to VI into ZC divided by R. Okay. So from here we can write down V0 equal to ZC by R multiplied by Vi. Here, now we need to put the value of ZC. Okay. The value of ZC we all know that is equal to 1 by J omega C. Okay. So just put this one. We can write down V0 is equal to 1 by J omega multiplied by RC into Vi. Okay. So this one in frequency domain. Okay. I already told you in my integrator and differentiator video that this 1 by j omega in frequency domain is same as integration in the time domain. Okay. So if you do the calculation, you can get in the time domain will be V0 will be 1 by RC integration Vi dt. Okay. So this circuit is nothing but a non-inverting integrator circuit. Okay. In the inverting integrator circuit, you can see there is a minus sign, but here you can see the minus sign is not there, right? It's a plus. That means this is a non-inverting integrator amplifier. Understood? And this is very simple. Here you can see the input voltage is in the non-inverting terminal. That's why we didn't get any minus sign. Okay. You can do this calculation in the time domain also. No problem in that one. What you need to do, in the capacitor formula, you need to use the I equal to C dVdt. Okay, so for that one, that will be little bit complicated. So I always prefer to do in the frequency domain. But if you have any issue with this one, maybe you can just tell me later. Okay. Now go to the next question. Find the output voltage for the given circuit. Very simple. This one I will solve in two ways. One is the conventional approach for the semester examination, and there will be in the JAM. Okay. If someone want to study JAM, maybe they can contact me. I will tell you what to do. For this one, first apply the KCL. If we apply KCL, then in this one, what will be the voltage? V2. Why? Due to the virtual short, right? So we can write down this is V2. If we apply KCL here, we can write down V2 minus V1 divided by R1 plus V2 minus V0 divided by Rf equal to 0. Okay. So from here we can write down V2 by R1 minus V1 by R1 plus V2 by Rf equal to V0 by Rf. Okay. So V0 will be equal to Rf multiplied by V2 by R1 minus V1 by R1 plus V2 by Rf. Okay. So that one equal to Rf by R1 into V2 minus Rf by R1 into V1 plus V2. So this will be the answer. Okay, this is a conventional approach. Now I will show you a simple approach. Now I will use a superposition theorem. Okay, when we apply the superposition theorem, we can do this one in two circuits, right? First circuit, I assume that V1 is short. This will be the one circuit. This is V2. This will be plus minus Rf R1 V0. Another one will be here V2 will be short, that means ground, and the voltage will be in the inverting terminal. Right? You all know the value V0 is equal to V2 into 1 plus Rf by R1, and here V0 is equal to minus Rf by R1 into V1, right? What superposition theorem say? Superposition theorem states that final output voltage will be sum of the contribution of the individual voltage. That means V0 is equal to V2 plus V2 into Rf by R1 minus V1 Rf by R1. You can see this answer is exactly same with this answer. Okay. Here, as I am doing for the first time, that's why I just draw both the circuit and I just show what will be the output answer, right? But here you can see you need to do a calculation to get this formula, right? When you are giving the JAM examination, at that time, by seeing the circuit, you can just delete this one and write down like this: V0 is equal to minus V1 Rf by R1. Okay, now just delete V1, write down plus V2 into 1 plus Rf by R1. This is the answer. So you can get the answer within 1 minute. Okay. Now back to the CU exam. Go to the next problem. In this question, there is two problems. One is the half wave rectifier. Okay. And another is a capacitor filter. Okay. Explain the operation of the circuit. So what I will do, first I will explain you the operation of the half wave rectifier. Okay, this is V0. First you need to understand two things. Here, if there is no diode, then you all know, if the diode is not here, this is just a voltage follower circuit with the unity gain, right? That means this is the Vi, so we can write down V0 is equal to Vi or equal to V0 sine omega t, right? That means when if the diode is on, then this particular circuit will work like this, right? And if diode is off, then how the circuit will looks like? What will be the value of V0? V0 will be equal to 0. Why? You can see there is no connection between the output of the op-amp and the V0, right? And as this is a open loop op-amp, that means there is no feedback. That means that this op-amp will work in the saturation region, right? And in the saturation region, there will be no virtual short. That means the V plus is not equal to V minus, right? And as there is nothing in the V minus, what will be the value of V0? V0 will be 0. Okay, so you already understand. If the diode is on, then the circuit will look like this. If the diode is off, then circuit will look like this, right? Now we need to see that when the diode is on, when the diode is off. Okay, first I just draw the sine wave. Okay, right? I assume that this diode is ideal diode. Okay, first assume that there is no capacitor. Okay, this is disconnected. Then we will show you the operation of capacitor. When the input voltage Vi is in the positive waveform, positive half cycle, at that time the input voltage at the V positive is positive, right? That means we give the input is positive, right? And we all know that the formula of V0 is equal to AD is V plus minus V minus, right? And we give the input voltage V plus is positive, right? And in the V minus, we didn't give any input. That means we will get a positive voltage at the output as we are giving the positive voltage in the non-inverting terminal. That means here we will get a positive voltage, right? And here we didn't give any input in the negative terminal, right? That means that is 0. So here we get a 0 volt, right? That means if this is V1 and if this is V2, then we can write down V1 is greater than V2, right? If V1 is greater than V2, then this diode D1 will be in the forward bias. Okay, as this is the ideal diode, with only this condition, this diode is in the forward bias. But if this is a practical diode, then what should we do? Then V1 minus V2 should be greater than 0.7 volt. That means when this input voltage is greater than 0.7 volt, at that time this diode will be turned on. But as this is the ideal case, when the Vi is just increased from 0 to positive voltage, at that time the diode will be turned on, right? And if the diode is turned on, I already show you that this circuit will be looks like a voltage follower circuit, and the output will be same as the input voltage, right? That means we will get sine wave in the output. Understood? No problem in that one. Now go to the negative half cycle. So for the negative half cycle, now the input is a switch from positive to negative, right? That means the value of Vi in this instant will be equal to negative. Okay, here the formula will be V0 is equal to AD into V plus minus V minus, right? Here V minus is 0 as I didn't give any input, okay? And V plus is how much? V plus is in negative. So eventually you can see here we will get a negative voltage, right? And we all know if we get a negative voltage here, is V, suppose this is a V1, get a negative voltage here, the diode will be off. Why? Suppose this is the diode and here is V1 and here is V2, right? And this is the negative voltage and V2 I didn't give any voltage, that means 0. So V2 is a higher voltage, V1 is a lower voltage. That means the current should flow from V2 to V1, right? But diode will not conduct in this particular condition. Why? In this case, diode is in reverse bias. Okay, that means diode will be turned off. Okay, and I already told you in the last slide, if the diode is turned off, then you can see this is the open circuit, right? That means the output will be 0, right? I just redraw that one again. Suppose the diode is off, right? That means the circuit will looks like this one. This is plus, this is minus, Vi and V0, right? Okay, so V0 is not connected with the op-amp output, and in the negative terminal I didn't give any voltage. That means V0 should be 0. So what we will get? We will get here is 0, and here again we will have a positive, and here we will again have a positive. So this will repeat, right? That means this circuit will act as a rectifier. Okay, so this will act as a half wave rectifier. Okay, so now you already understand the work of this particular area without any capacitor, right? And with this particular area of the circuit give us a rectifier, half wave rectifier. Okay, so what we need to do now, we need to draw the circuit again for the capacitor load. Here the load is capacitor, right? So here we can draw that we have a voltage source, here is Vi, okay, and we have a capacitor, right? And here this Vi is the this input voltage. Suppose this is Vx, so this is Vx, okay. So Vx is nothing but a half wave rectifier output, okay. So that means what we will do, this will act as a capacitor filter. And how it will work, I already have a dedicated video for the capacitor filter. I will put that link in the description. Please go and watch that one if you didn't understand here. Okay, I will explain you again in this one. Suppose I redraw this one. Okay, this is Vx, and here we have like this. Okay, and suppose this is the output we are drawing. So this is V0. So I just do a dotted line of the input voltage. Now you can see here. You all know capacitor is act as a battery, right? That means the capacitor will charge with a particular voltage. And you all know that when you add a capacitor in a circuit, then the voltage will build up like this, right? That means when you add a voltage source into the capacitor, then the capacitor will charge with that particular voltage, right? That means if I take another color, then when the input voltage is this, then capacitor will take the voltage and do the charge, okay? And it will go up to this line where the input voltage is maximum, okay? Now see this. Here you can see for the capacitor in the charging cycle there is no resistance R equal to 0, right? That means the time constant for the charging is very fast, is 0. That's why it will exactly follow the input voltage curve. Okay. Now for the output also you can see the output R is infinite as there is no resistance in the output. So the time constant for discharge will be also infinite. That means when the capacitor will fully charge in this point with the maximum voltage, after that there is nothing for the capacitor to discharge, right? So the capacitor cannot discharge as the resistance is here is infinite. So there will be no current flow through the resistance, right? That means the capacitor will not lose any of the charge, right? That means the capacitor voltage will be kept constant and it will be constant like this as there is no resistance in the output, okay? But suppose you have a resistance here, then what will happen? Then this capacitor will discharge with the depend upon the time constant of the resistance like this. Suppose this resistance is R1 and this resistance is R4. So we can write down R4 should be greater than R3 should be greater than R2 should be greater than R1. Okay, so this will be the answer. That means if we do the whole thing together, then what we will get? This will be the input voltage. So the input voltage will be sine wave okay, and the output voltage will be how? The output voltage will be looks like this one. Up to the first peak, it will go or follow the input curve, okay, and then it will be kept constant. Okay, so this will be the output voltage. So this is all about this circuit. In all of this previous question, this is the only question that is little bit difficult. Other is everything is okay. If you didn't understand this problem, please let me know. I will explain you again. So now what we need to do? We need to simulate this circuit and see what will be the output voltage. Okay. At this instant, I didn't connect the capacitor. I just connected resistance, okay? Normal resistance, just to show you that what will be the output voltage, okay? And here you can see that there is a three voltage. One voltage is this one, another voltage is this one, and another one is the output. The blue one is the output voltage, okay? And the green one is the just before the diode at that particular node, what is the voltage, okay? And the orange one is the input voltage. If you see the output voltage at the just before the op-amp, the green one, you can see this will follow a sine wave, okay? When the diode is on. When the diode is on, this particular circuit act as a voltage follower. So it will just follow the input voltage, right? You can see here, just like that input voltage. But when the input voltage goes to the negative half, at that time you can see the positive terminal. At that time, I already explained you, at the positive terminal, we are giving the negative voltage, right? That means the output should be negative. So you can see the output of the op-amp is minus 15 volt. That's why the diode will be turned off. If you see the top waveform, that is just the output after the diode, and you can see that is a perfectly half wave waveform. Okay, so if I just do in a same one and I just delete the this one, you can see the blue one is the output voltage and the orange one is the input voltage. Okay, orange one you can see, we can see the full sine wave, but in the blue one you can see the half sine wave. Okay, so this is the circuit without a capacitor. So what we need to do? We need to connect a capacitor. So now you can see here that the output voltage is constant. Why? When the just circuit started, at that time the blue line is just follow the orange line. That means the input and output is the same. Okay, and when it just go reach to the max one, the peak, then capacitor don't have any path to discharge the voltage. Okay, discharge the charge, right? And as there is no path to discharge, the capacitor will hold it voltage, and you can see this one, the output is the constant. Okay, now I will show you if I connect a resistance, then what will happen. Now you can see it looks like that it follows the same path, right? But it depends upon the resistor. As you can see, the resistor is already 10K. Now, if I decrease this value, very beautiful, right? As you can see, it's only 10 ohm. So it is discharging through the 10 ohm. Now, if I just increase a little bit, you can see the slope is increasing, right? And if I just decrease that one, you can see, right? You understand? So the slope of that one is completely dependent upon the resistance, right? And if that resistance is too much high, like 10K or 30K, you see, it's just the constant, right? So in the CU exam paper, they just provide us the capacitor with the infinite resistance, right? That's why it will be, output will be constant. Okay, think you understand the concept. Okay, you don't need to write down everything in the paper. This is just for your concept. Okay, in the paper, just do the calculation, just so that this is the half wave rectifier. I connect a capacitor filter, and as this is a capacitor filter without any resistance, then there will be no discharge, as the discharge time, if time constant, will be infinite. So it will just a peak detector circuit. Okay, now this is the last problem. Okay, this problem came in the 2013 question paper. Okay, Here you can see this is just a integrated circuit, right? And if I do the calculation, we all know V0 will be minus 1 by RC integration Vi dt. This is the formula, right? But as this is a CU question, so we need to derive the expression. If we apply the virtual short, then this point will be 0 volt, right? And if we apply the KCL in this particular point, we can write down 0 minus Vy divided by R plus C multiplied by d0 minus V0 divided by dt equal to 0, right? From here we can write down minus Vi by R equal to minus C into d minus V0 by dt, right? From here we can write down V0 will be minus RC integration Vi into dt. So this is just an integral circuit, okay? And we already have the formula V0 equal to minus 1 by RC Vi dt, okay? And here they told us the input will be looks like this one, okay? And we need to sketch the output from t is equal to 0 to t is equal to 6 milliseconds. Here you can see t is how much? From 0 to they provide us 5, right? 2 and 5, that means up to 6, that is 0, okay? So you can see here we need to divide this one in the three part. First, Vi equal to 0 within when t is 0 to 2. Vi is equal to 1 when t is 2 to 5. And Vi equal to 0 when t is greater than 5. Right? Now you can see here. First we need to input the resistance. We need to put the value of resistance. So R will be 100k into 10 to the power 3 and C will be 10 nanofarad, that means 10 to the power minus 9 into Vi dt, okay? So if we just do the multiplication, we can get 10 to the power 3, 10 to the power 7, 10 to the power 6, right? That means 10 to the power 3 multiplied by Vi into dt, right? So you already got the output voltage. Now we just need to put the value. First, what we need to do? We need to do the integration here. So I just go to the next page and we already got V0 is equal to minus 10 to the power 3 multiplied by integration 0 to t Vi dt. Okay. Now we need to distribute this one to the three part. One is this part, another is this part, and another is this part. Okay. So the first limit will be 0 to t Vi into dt plus 2 to 5 Vi into dt plus 5 to infinite Vi into dt. Okay, and you can see here this part is 0 and 5 to infinity is 0. That means this part and this part will be 0 and 0. Okay, so we will get only the value of V0 will be minus 10 to the power 3 2 to 5 integration Vi into dt. Okay, so just now we need to do the integration here. Minus 10 to the power 3 Vi, the value of Vi is how much? 1, right? So that means we will get 2 to 5 millisecond, this is in millisecond, into 1 into dt. Okay, so we can write down V0 will be minus 10 to the power 3 2 millisecond into 5 millisecond 1 into dt. That means equal to 10 to the power 3 equal to t from 2 10 to the power minus 3 to 5 into 10 to the power minus 3. Okay, so we will get minus 3 into 5 minus 2 10 to the power minus 3. Okay, so that means we will get the value of minus 3 volt. Okay, that means we will get the value at 5 seconds will be minus 3 volt. Here you can see the expression of the output will be t when the time will be 2 millisecond to 5 millisecond. Okay, and the minima is how much? Is 0 and the maximum will be how much? Minus 3. So the how the output will looks like? The output will looks like, if I draw here, then up to 2 millisecond that will be 0. Okay, up to 2 millisecond the output will be equal to 0. Okay, and then from 0 it will go to how much? It will go to minus 3. Okay, it will go to minus 3. Okay, and then it will come back again to 0 and go like this. Okay, and this will be minus 3 volt, this will be 0 volt. Okay, so this will be the output. This one is from the integrator, right? And maybe the question comes from the differentiator. So what we will do, I already did one question that is came in the JS 2023, I think. I already solved that one where they provided differentiator circuit and they provided a triangular wave, okay? And we need to derive the output expression, and that will be the square wave. I already have that kind of video. Please go and watch that one, okay? So that's all for this previous year question for the OPAMP. So I already completed all of the previous year questions, like from circuit theory, from Zener diode, from transistor, and from also the OPAMP. Now your work will be just go through all of this video, okay? And please let me know if you have any kind of problem. I will always there to help you. Okay? Thank you. Bye bye. Thanks for your time. Please do share this concept with your friends. And if you like this video, please press the like button. It is really means a lot for me. Bye bye.